a subset U of R is open if the following happens, right? If for each x in U we can find some positive number epsilon such that the ball numbers. So in this set, can I find the rational number between x minus epsilon and x plus epsilon? You guys, second yes, can I find it?
So you're asking if you can find the rational number
In this set. Can you find it? So remember that recently or last year you spoke about the density of the reals. That between any real numbers there is irrational and there is also rational. So I know that the irrational part we don't do it in 2 to 0. So it is there. You can prove it easily. So yeah, this is what I wanted to record. And then we get a proof. And then let us look at now in general the examples. I see that the more I use this thing, the more I can't write properly. Examples of open sets. Right. So, and one thing you should know, this approach that we are taking, since in our data you don't have open, because it's open.
You can prove it by saying, assume it's not open, and then you prove that that's false, therefore it's open.
But can you use this definition?
False backwards. For each x, there are no x, that was true for all x in
Okay, good. So this are the open sets. It's interesting one. This one I would like you to engage. So let's take the set Q of rational numbers. Is it open or closed?
So, because if you took like epsilon to be square root 2, then it wouldn't be in the set. So then,
But what does the definition say?
it says for each x, so if I could choose any x to be a rational number, then if I choose any real epsilon, so I can choose my epsilon to be whatever I want. So I'll choose it to be an irrational number.
Yeah, but you can't choose it
Yeah,
as
because
well to
rational
100,
doesn't make
because epsilon doesn't make sense if it's 10. Or does it make sense?
You just said there.
Yes.
Sorry, sir. I think it's not closed or it's not open because of that density thing. Like for between any two rational numbers, there's some irrational number, and between two irrational numbers, there's an irrational.
So if you get a set like this, it will be in Q, right?
Yes.
It won't be in Q necessarily because you're going to have irrationals. So that's why it's not.
Oh,
Yes.
Oh, okay. Yeah.
So the thing comes from there.
Yeah.
That between.
because the Q set will only have rational numbers,
Yes, so-
irrational numbers
yes,
between. So
yes.
you can't engage with.
So you see, that's why I spoke about the density first, because I know that you're going to use it there. So you understand how you use the definition. So this is not open. It's not open. That now say is open. So this is not open. So we understand the idea now, right? Probably. So, and then what about this one? The set R without Q. This is set of irrational numbers. Is it open or not?
Without rationals.
Yes, we use it.
Only irrationals.
Yes.
So we'll never be able to get rationals.
So is it open? Please guys, let us have a discussion.
It's not open by the same logic.
Well, if you take another set like this set contains rationals, which is not in you.
You've removed the rationals.
No,
You've
it's the
removed
set.
the rationals.
Yes,
You've removed them.
yes.
And they are out, they're not in the set anymore.
Yeah.
Right? In the real number line. They're not in the set. You've taken them out.
Yes,
And all that is left is irrational numbers.
yes.
And I understand
But
this.
how do you define this?
Because there's just irrational numbers in the set, it's fine.
No, it is not like that. It says that
So the problem is what happens if our
Yes.
distance definition of basically.
this one,
What happens if our distance is rational?
the one that it
It's
contains
fine. There's
an
still
open
between any
ball.
two rational numbers, there's an irrational. Between any two
Remember
irrational
that-
numbers, there's a rational.
But you've taken the rationals.
No, you
irrational
take.
Yeah,
If
but
you take.
we're looking, our total spaces are.
Yes.
part. Yes, total spaces are.
Yes.
The set is open.
We've taken out the rational numbers. We've taken them out. They're not in the set.
Yeah.
They're not in between any irrational numbers.
Yes.
They're out.
Yeah.
They're out. They're
No,
not in the
if we're
set.
looking at that set inside R, if we were looking at just that set, if you put some metrics on the irrationals or something, that's different. But there are still the other ones. We're just looking at the specific ones that aren't that. We're just looking at the irrationals now.
Okay.
Inside the real numbers.
So we're taking real numbers and then looking at all the irrationals
Yeah.
inside the real numbers.
Let us go back to
So if it's affected epsilon,
what do you
then get
understand by the
irrational.
density of irrationals.
So then that's me.
So,
You say between any
yes.
two real numbers.
Numbers.
Alright. So I take x in R without Q. Right? And then I get some epsilons positive. They should be irrational, right? And the density of rationals,
It should be
Irrational.
they should be rational numbers.
Yeah.
So this can be in that set. So this can
Okay,
be
maybe I'm not hearing it right, sir.
what?
In that set,
I take x here. This x is not irrational.
It's not rational.
Yeah, it's not rational. Yes, sorry. Yes, it's not rational. Then, by that definition, I have to get some epsilon positive, so that this set it contains in there.
I see that, sir.
Yeah.
My
But-
question is, you see that R, that set we made there, that R, Q. What does that set? What is that set?
A set of irrational
It's
numbers.
R line Q, so real non-rational.
So it's all the real.
Not rational.
Yes.
Yeah.
There's no rational numbers.
Yeah.
in that set.
Yeah.
Yes.
There's no rational. There's no rational numbers.
Yeah.
Yes.
But now that but in all of those balls of radius epsilon, there is a rational.
Wait, are we saying that?
This x is not irrational. It's not rational.
Yeah.
But this one is a real number,
Yeah.
and this one is a real number.
Now that's
This is less than that.
Oh, okay, wait,
Between
are we-
these
are we-
two, they should be rational.
Are we saying from
I
X?
hear that there.
Yeah.
So are we saying X epsilon?
Yeah?
There's another way of explaining it.
That's
Okay.
what-
Let's use the open ball. Because now I'm reading
That's
it on
it.
the internet and it says that. Because no, this is just being overcomplicated now.
Alright.
If the
So,
open ball
Kuselo,
centered at the point-
The
Wait, I have
the
a question.
open ball you're talking about is this one, right?
Yes, that's the one. I'm
It's the
Which
same
is
thing.
this one?
That's the same thing.
Yeah. That is the open ball.
So I have a question regarding.
I'm defining the
Okay,
opposite
okay.
so that C I can stop writing with.
Alright.
I just figured it out.
You see what I'm
I
saying?
just figured it
Now
out.
it's
No,
done.
check this.
Yeah.
Check this. That epsilon is a real number. It doesn't follow the rules of the few set that's made here.
Yes.
So when you put epsilon and you minus x, whatever, even though it's not in that ball will not be
Yes.
contained in that set because epsilon just breaks everything. That's it.
So we're clear now.
Yes.
Alright, good.
Right? It's from that set.
Yeah.
Right? Oh, wait. Ah, flip. Wait. So we're looking at that ball. Oh, that ball we're seeing if it fits in that in the set.
Yes.
Okay, sharp, yeah.
Okay.
Got myself again. Now, this is what I'm saying. You take X, it's from that set.
Yeah.
You take epsilon, it's from that set.
It can
Yes,
okay,
This
fine.
one, yeah.
Alright,
Yes,
let's say
keep going.
Then, won't that make it open?
No.
no, because that ball will still contain a point that's not in that set.
Because that
Okay,
set is
one
also...
line.
Then it's open. You have to prove that that.
Sir, can I write this down?
Yes.
So, this is what you did. This set
Yes.
is the set of real numbers without any rationals, right?
Yes.
Yes.
All the rationals,
Yeah.
take them out from the set.
Yes.
Now there's no rationals. They're in this ball now. They you see, they're not
Okay,
here
they're not
anymore.
there. That's yeah.
They're not in this. They're not in the set anymore. They're gone. You
Yes.
take them out.
No, leave it.
They're here now, right?
Yeah.
Okay.
Right?
Yes.
Serious.
Now what's left in this?
Wait,
No,
wait,
what's left in the set now is the rational numbers,
Go.
right? No, you have your theorem of density, whatever, right? So this is A, and between A, like C, between whatever, this D, the C,
Yeah.
it's a rational which has been taken out from the set. It's not there.
No, you're right. You're right. In the space of irrational numbers, that okay. The thing is, you're not looking at that set as
in
itself.
R.
You're looking at that set inside another set.
That's what's confusing me.
Yeah.
Yeah.
So the
Because look, it's inside R, right? So we're looking at all the dots inside. Well, okay, all the
Yeah.
irrationals inside R.
Yeah.
So inside R, they are still rationals.
Yes. So
If you looked at it, if you just looked at that set, then that ball would be open.
Yeah.
Oh, we still look at the set
No,
in
we're
R
not.
still.
In R, yeah.
Yeah.
Oh,
You
that's
don't
right.
take them out. You don't consider them.
Yeah, you just say, kind of, I don't know, you could say, look at a square inside the plane. You don't ignore the plane.
Oh, I thought you take them out.
Just say that so other people don't get confused on what irrational is.
Nah, I thought you see that's what
Alright, so this one we can accept, but we are going to do a proof now. And then here, an intersection of a finite collection of open sets in R is open. It is an open set. So, the second statement, you believe it? Hmm? The other one we just take an arbitrary collection. The union of arbitrary collection. And then when we take the intersection, we need them to be finite. Who can give me example that shows that if we take the intersection, we need to consider the finite collection, not an arbitrary collection?
Consider all the balls around the point. The only point that's in every single ball around the point is the point itself, which is not open.
What will be your counter example? What kind of set? You just say singleton.
Okay, an intersection of finite.
And then how do you take the intersection?
You very epsilon.
Well, okay, the intersection for all epsilon.
You vary epsilon. Right. So if we take the intersection,
the smallest one will be the intersection of all the ones.
but that is not the point, right?
What is
No,
this?
it's not the point. It's the one that's closest to the point. Because epsilon
Yeah, but
cannot
that
be
is
on
not
that
the-
side.
Okay, epsilon, all epsilon greater than 0.
Yeah,
Yeah.
that's going to be a point.
It's going to be around the point.
Is it going to be a point?
No,
If we take epsilon, we take that as 0.
It's not going to be a point.
it's
It's
the
going to be a
smallest
set.
one. It's the smallest ball around the point, but
It's
it's
going
not.
to be a set.
What is the smallest ball? What is the smallest?
It's the smallest set at around that point. It's
What
not
is the
gonna.
smallest set around?
I don't
yeah,
know.
okay, like
The smallest set around the point is just the
epsilon
point.
should be positive.
And the
Yes.
point isn't open.
But epsilon cannot be.
So it will be.
Okay, so pick a point. Let's say a point that is 0.001 away from our starting point.
Yes.
Pick epsilon equal to half that distance.
Yeah.
Then that point's not in that, and it's not in our intersection.
Wait, what?
This one is a
You
color we
can
can
always make it smaller.
Yeah, you can always make it smaller than any other set.
But isn't our
Yeah.
thing a set?
There is no smallest set.
There's no smaller set.
Is X a singular point?
But if you're taking it this way,
Oh, that's why it has to be finite at some point.
Yeah,
Yeah, it
that's
has
why
to
we have to
be.
have, if it's finite then you're right. But this is an infinite intersection and it gives us a closed set.
Yeah.
Which is why we need finite.
Yes, that's yeah.
what will be the good example here?
Is that not the counter example?
Hmm? Yeah, but what is this X anyway?
Looking at this guy.
Okay, for more interesting mathematics, watch part 2 of this video.
Yeah.
Oh yeah, you get